Unit 3 notes day 2. We are taking a look at one specific type of free response question that deals with separating the variables. It does pop up on the multiple choice section sometimes as well. So this one says solutions to the differential equation dy dx equals xy cubed also satisfy, it gives us the second derivative. Let y equals f of x be a particular solution, and we know when x is 1, y is 2. So part A wants an equation of a tangent line, right? An equation of the line tangent to that particular solution at x equals 1. So we know the point is 1, 2, so there's our point. We need the slope. Slope is dy dx. So plug in 1, 2 for x and y. So our slope is 8. So we can write an equation of the tangent line. And there's our tangent line. That's part A. Part B says use the tangent line equation from part A to approximate f of 1.1. So plug in 1.1 for x. Probably the easiest place to usually plug it in is right here, because this value is usually pretty close to the x value that's given. So y minus 2 equals 8 times 1.1 minus 1. So 2.8 for part B. Given that f of x is greater than 0, for x is between 1 and 1.1, is the approximation greater than or less than f of 1.1? To tell if a tangent line is above or below a curve, what you want to do is you want to check its concavity. If I have a graph that is concave up, the tangent line is always under the curve. That's a bad tangent line. If I have a graph that's concave down, the tangent line is always above the curve. So really what we need to do is we need to know, is the graph concave up or concave down at 1.1. Notice it says the y value is always positive. So this is positive. Our x value is positive. Our y value is positive. 1 plus positive. All this is positive. The second derivative, d squared y over dx squared, is greater than 0 at x equals 1. Therefore, the tangent line is under the curve. So the tangent line, the approximation is less than f of 1.1. Basically, the point on the graph is above where we approximated it to be based on the tangent line. Part C. Part C wants the particular solution. This is the type of problem we're focusing on here today. It asks us to find the particular solution y equals f of x with the initial condition f of 1 equals 2. So to get a particular solution, I need to solve for y. Basically, it wants to know what y value, y equals what, has a derivative of this, and also passes through this point. Because the derivative is in terms of x and y, in order to integrate it, you have to separate the variables. So all the x's need to be on one side, and all the y's need to be on the other. So we've got dy dx is equal to xy cubed. I'm going to multiply the dx over. Oops, I left the x off. And divide by y cubed. Next, we integrate both sides. Rewrite that as y to the negative third. Remember, we have plus c on this side and plus c on this side over here. Usually we just put the plus c on the side with the x's. We want the particular solution with the initial condition 1, 2. So let's solve for y here. So I'm multiplying times 2, and then also multiplying by y squared. We need to solve for c. Might be best actually to solve for c in this previous step. So when x is 1, my y value is 2. So if I plug in 1 for x, 2 for y, c equals -5/4. That's gross. So at this point here, we have -1 over x squared minus 5/4 equals y squared. We want to multiply the top and the bottom by 4 to get rid of this fraction on the bottom here. And then square root. Remember, we do technically have plus or minus, but when we plug in 1, we want to get +2. So if I plug in 1 squared, 1 times 4, 4 minus 5, -1, -4 divided by -5. I want to get +2 out of that. So technically it's plus or minus, but because my point's 1, 2, it should just be the positive one out front. That's the same problem again. And then this is the other one I want to take a look at. We're not going to do the whole ABC because A and B are pretty similar. But in part C, it wants us to find the particular solution. And one like this you need to be careful about because a lot of times people treat this B as though it's an X value. Notice B's in the numerator here, dy, dx. Xt is my X value, our dependent variable where y usually goes as a B. So we're going to treat this as though it's a y. And if the derivative's in terms of a y, that's when you have to separate the variables. So when we separate the variables here, I'm going to leave the 1/5 on this side. Technically, you could also move it over. So we divide both sides by 100 minus b. This side, when I integrate, I get 1/5 t plus c. This side, we're officially u substituting, although you might be able to do it without, because du is just -1 db. So I need a -1 and a -1. There's my du. Absolute value of u, which is 100 minus b. Divide both sides by -1. E to this power plus c, and remember that plus c, when I have it in the exponent, I can move it out front. Minus 100, and then divide both sides by -1. It's going to change it to plus 100. And then we can plug in our point. 0, 20. 0, that'd be e to the 0, which is 1. So b equals -80 e to the -1/5 t plus 100. So a couple things going on in this problem that were a little different than the last. Remember, when you have ln and you change it to exponential form, the e to the whatever plus c, that plus c can be moved out front. It's a different constant than this constant here. And then also making sure if it gives you something other than x and y, double check, is that an x value or is that a y value?